Have you ever wondered how to design a robust and efficient OO program? Well, you're in the right place. Object-oriented programming, or OO programming, is a paradigm that uses objects, which can contain data and code, to design applications and computer programs. It's pivotal in software development, enhancing flexibility and making code more resilient and maintainable. The process of OO program design involves several steps. First, we define the problem and understand the requirements. Then we identify the objects and entities, and define the classes and attributes. Next, we define methods and behaviors, establish relationships, and set up an inheritance hierarchy. Furthermore, we delve into polymorphism, encapsulation, and design patterns, before finally modeling behavior, documenting, testing, validating, and implementing the design. Each step is crucial, building on the last to create a comprehensive, efficient, and robust OU program. Now that you know what to expect, let's dive into the first step, problem definition. The first step in designing an OU program is problem definition. It's like charting your course before setting sail on a journey. You need to clearly define the problem you're trying to solve. What is the purpose of your program? What does it need to do? Gathering information about the problem domain and identifying key stakeholders is crucial at this stage. You need to understand the requirements thoroughly, because only then can you determine the scope of your project. And by scope, we mean the functionalities that need to be implemented. It's a bit like drawing up a blueprint for a building. You wouldn't start construction without it, would you? Defining the problem clearly and determining the project scope sets the stage for the next steps in the OEO program design process. Once you've defined the problem, it's time to identify the objects and entities. Next, we need to identify the objects and entities in the problem domain. This process is known as entity analysis, where we examine the problem domain to identify real-world entities and objects along with their relationships. Here, we're essentially trying to map out the landscape of our problem, detailing the players involved and how they interact. Now, a handy trick during this phase is to look at use cases or user stories and identify the nouns and verbs. Why, you ask? Well, nouns often represent potential objects, while verbs can give us a clue about methods or behaviors that our objects might need to have. For example, if we have a sentence like, a user posts a comment, user and comment become potential objects, while posts could indicate a method. With our objects and entities identified, we can now define our classes and attributes. This sets the stage for the next step in our object-oriented design journey, defining classes and attributes. Now we come to the step of defining classes and attributes. This is the phase where we give form to our identified objects by creating classes. A class is like a blueprint or a template that encapsulates related attributes and behaviors. For instance, if we're designing a car class may encapsulate attributes like color, make, model, and behaviors like start, stop, or accelerate. Each class should have a clear purpose, and its design should be guided by the principle of cohesion. That is, it should represent one single concept or entity. Next, we define attributes or data members for each class. These attributes represent the state of objects. Going back to our car example, the color, make, and model are attributes of the car class. Remember, the aim here is to design classes that are self-contained, reusable, and have a single, clear responsibility. Once we've defined our classes and attributes, we can proceed to define methods and behaviors. Defining methods and behaviors is an essential step in OO program design. At this stage, we identify the actions or behaviors that the objects of each class can perform. These behaviors are represented as methods within the class. For example, a dog class might have methods like bark, run, and eat. Each method should reflect a specific behavior that an instance of the class, that is, an object, can perform. Next, we assign responsibilities to our classes. This is where the Single Responsibility Principle, or SRP, comes into play. According to SRP, each class should have one, and only one, reason to change. In other words, a class should handle just one part of the software's functionality, promoting cohesion and minimizing coupling. From identifying behaviors to defining methods and assigning responsibilities, each step helps us build a solid structure for our OO program. After defining methods and behaviors, we need to establish relationships among our classes. Establishing relationships and inheritance hierarchy is a crucial step in OO program design. Diving right in, let's talk about association and dependency. Association is when one object is linked to another. either through a one-way or a two-way connection. It's like being friends with someone. You know each other and interact, but you're not reliant on each other to exist. Dependency, on the other hand, is a stronger relationship. It's more like a car and its engine. The car can't function without the engine. One class depends on another, meaning if one changes, the other might need to as well. Now it's time to uncover commonalities among objects. This is like a group of friends discovering they all love the same band. They share a common attribute, their taste in music. In programming, we identify common attributes and behaviors among objects and use inheritance to create a hierarchy of classes that share these common features. This helps to reduce redundancy and makes the code more efficient. Next, we move on to base and derived classes. Imagine a general category like animal. This is our base class. It has attributes and behaviors that all animals share, like eating and moving. However, a dog, a type of animal, might have additional characteristics such as barking. This is our derived class. It inherits all the attributes and behaviors from the base class animal and adds on its unique features. Designing a base class with shared attributes and behaviors and creating derived classes that inherit from the base class helps to organize our code, making it easier to understand and maintain. It also allows us to reuse code, which is a key principle in software development. Now that we understand relationships and inheritance, let's move on to polymorphism and encapsulation. Polymorphism, encapsulation, and design patterns are important concepts in OO program design. Let's dive in. Polymorphism is all about one name, many forms. It's the ability of an object to take on many forms and behave differently in different contexts. There are two types of polymorphism: method overloading and method overriding. Method overloading is when we have multiple methods with the same name, but different parameters within a class. On the other hand, method overriding is when we have a method in a derived class that overrides a method in its base class. This allows us to implement specific behaviors in derived classes. Moving on to encapsulation, this is a key principle that combines data and the operations that manipulate them into a single unit, a class. Encapsulation is all about data hiding. It's about encapsulating the internal details of each object by defining private attributes and providing public methods, also known as getters and setters, for access. This helps to maintain the integrity of the data while providing controlled access. It also lets us determine the appropriate access control for class members, whether they should be public, private, or protected. Lastly, let's talk about design patterns. Design patterns are tried and tested solutions to common design problems. They provide a way to structure our classes and objects to solve specific types of problems. For instance, the singleton pattern ensures that only one instance of a class is created. The observer pattern allows objects to notify other objects when their state changes. And the factory pattern provides a way to create objects without specifying the exact class of object that will be created. Applying these design patterns helps in creating a flexible and maintainable code base. And as we continue to build our program, we should always be open to refactoring our design to improve its clarity and adherence to design principles. We've covered a lot of ground. Next, we'll look at modeling behavior, documentation, testing and validation, and finally, implementation. These final steps help ensure that our OO program design is robust and efficient. State and behavior modeling are vital for defining how objects interact and change over time. Event-driven programming allows our system to respond to user actions or system events. Documentation is the unsung hero of any project. Code comments clarify complex logic, while unified modeling language or UML diagrams visually depict our classes and relationships. Testing is another essential step. Unit testing verifies individual pieces of our program, while integration testing ensures these pieces work together harmoniously. Once we've tested and validated our design, we move on to implementation. This is where we bring our design to life, meticulously crafting classes and methods. Version control systems, like Git, help manage code changes and foster collaboration. That wraps up our guide to designing a robust and efficient OO program. Let's recap what we've learned today. We began with problem definition, understanding the requirements and scoping the project. Then we moved on to identifying objects and entities, using entity analysis and the nouns and verbs approach. We defined classes and attributes, encapsulating related behaviors and data members. We looked at methods and behaviors, assigning responsibilities and defining actions. We established relationships and dependencies between classes and objects, and built an inheritance hierarchy, designing base and derived classes. We explored polymorphism through method overloading and overriding, and encapsulation with data hiding and access control. We applied design patterns like singleton, observer, and factory, and discussed the importance of continuous refactoring. We modeled object behavior, used event-driven programming, and documented our design with code comments and UML diagrams. We tested and validated our design through unit and integration testing. And finally, we implemented our design using version control systems. Remember, practice makes perfect. So go ahead and start designing your own OU programs. Happy coding!